just don't feel like writing the paper. So if you do,
Oh.
you can put your name on it as co-author. It's just I don't know. But this is like alright.
If you go to Unit 2, to Chapter 8 of Unit 2,
It's not a big deal.
so it's almost like here. Yeah. So your cost should look similar to this.
Okay, the lecture today is mostly the nonlinear algebra, or linear algebra and some nonlinear effects that involve the main topic, which is resonance of systems that are coupled to each other in various ways. I should point out that the textbook has a lot of what is in this lecture condensed. This is going to be adding water so that it swells up and hopefully makes more sense. But in any case, the main thing today is to figure out how to handle projection operators in eigensolution arithmetic and algebra that is really very powerful. This projection operation business that I'm showing you today is a real doorway to getting into the symmetry algebra and group theory more efficiently as it is applied to physics. Indeed, much of what I've done in that field would have been impossible without these techniques. So we're going to just take on something really simple, and that is a unsymmetric matrix. This is a case where we're really going to see for the final time the idea of duality between bras and kets, but this time it's much simpler. It's a simplifying way of looking at all of that. So let's go ahead and get into this, and this takes a bit of time, and we may have time to actually use it on the problems that are being showing down here. So this sort of thing that we looked at last time, coupled oscillators, in this case in 2 dimensions, but this is a method that works for any number. You probably are aware that we were the first in this laboratory to do the complete analysis of the fundamental modes of the buckyball before it was discovered, and the result was that it helped to discover it because spectroscopy does that. In any case, we'll stick with 2 dimensions here rather than 60 times 3, 180 dimensions that involve the resonances of the classical modes, fundamentals of that monster molecule. The basic idea is that I want to take a matrix that's n by n, but here's the example that we're going to use: 1, 2, 3, 4, starting in the upper right-hand corner and just going 1, 2, 3, 4. You get a matrix that has nice integer eigenvalues and some vectors that are easy to see in the way we're going to display them. But the basic idea is that we've got to find a way to find a new basis, and this is what quantum mechanics is really all about nowadays, is that you have some Hamiltonian matrix that you need to have this done to it, that is re-base it, find a new basis for it, in which we use little epsilons usually because that's Greek E for energy, but whatever your symbolism is, the idea is you end up with a matrix, and usually it's a symmetric matrix or Hermitian matrix, so all those numbers are real, but we're not going to have that restriction. This method is powerful enough. It's as powerful as the 4-wheel drive garbage truck that we talked about before. It takes you anywhere and carries a load of junk with you. So basic idea, of course, is getting the actual numbers that are there. Those are called the eigenvalues. And just to give you a feeling for how we have to do a secular equation, that's the name of the equation that gives us those eigenvalues. here's a very simple way to see it with a 2x2 matrix. Here's the Eigenvector equation set up. This is claiming that I can find a set x and y components of a vector such that when this matrix is applied to it, it gives that vector back again with its length changed, possibly. If epsilon is equal to 1, then it just gives the vector back again. We'll see plenty of operators that do that sort of thing. But that then reduces to an equation here, which we solve by Kramer's inversion. You know how you replace the inhomogeneous part of the this equation with a that is, you replace the first column of the matrix that you were trying to solve here with those two numbers, and then to get the other solution, y, to this equation, you would do the same thing with the second column. But the problem with that, of course, is you know right away that this is just giving you an answer x equals 0, y equals 0. Nobody's going to pay you for that. It's a correct answer in the sense that it is an eigenvector of this matrix, but it's an eigenvector of every single 2x2 matrix in the world, right? So we got to do better than this, okay? And that better than this is called the secular equation. So that's the next thing that we need to do. Now I want to follow these guys along because we'll be looking at examples as well as the mathematics for this stuff that is a little bit intricate, so it helps to have it, first of all, on a brighter screen. So in any case, the deal here is that maybe I mean, if I gave that to my employer and say your answer is x equals 0, y equals 0, you're either fired or go back and get a better answer, and then you realize that if I could make this denominator 0, then I have a chance of getting an answer. Otherwise, no chance. So this is the equation that is very important for this sort of thing. It becomes an algebraic equation involving the determinant that is written here, the determinant of this matrix, 1, 2, 3, 4, minus the unknown epsilon times the unit matrix. So in this case, as you can see, this one comes out very nicely. Well, we'll see later that it comes out nice. I'm just writing it all out here. The product of this times this minus 3 times 1. That becomes a quadratic equation, epsilon squared minus 6 epsilon plus 5. Now, for the 2x2 matrices, remember there's a really simple way to get that equation. The first order component here, that is the coefficient of the epsilon to the first power, is the trace of this matrix. This matrix trace is 4 plus 2, the sum of the diagonal elements. So that's the 6 right here by more laborious algebra. And then the multiplier of the constant in the polynomial is always the determinant. So this is true for any matrix. The first one and the last one are things that we know and love, trace and determinant. In between that are sums of diagonal minors. So learning, that's one of the things that you should become familiar with, the diagonal k by k minors for the kth case. Starts with a trace, which is the 1 by 1 minors, and then the one single minor that this matrix has, which is its determinant, is the last coefficient. You have to be careful with the parity of the sign, but aside from that, that is a simple way, and we'll use all of this stuff later on in a discussion in the next lecture when we take on more pathological matrices than 1, 2, 3, 4. Okay, so this is the starting point of finding eigensolutions. Resolving a matrix is another name for this. The main idea is the fundamental theorem of algebra says that if you do have an nth order polynomial, that if you're allowed to use complex numbers, you're guaranteed to be able to factor that into an algebraic set to give solutions. In this case, epsilon minus 1 and epsilon minus 5 are the two factors. Eigenvalues of 1 and 5 are what we're going to be dealing with as we discuss this little 2x2. So that is the main idea here, and then comes a theorem which is actually quite difficult to prove in general. But it's obvious if it's given that your matrix can be reduced to this form. Because then the secular equation of this matrix, and that's the whole idea of this theorem, is that each epsilon in the secular equation, either in its unfactored form or in its factored form, if you replace every epsilon by the matrix itself, and that's what we're really doing right here. We're taking our equation epsilon squared and replacing it by 1, 2, 3, 4 matrix squared. And then minus 6 times epsilon was minus 6 times the whole matrix. And then finally the 0th power of the matrix, that is the unit matrix, takes up the rear guard right here, and 5 times 1 is just 5 times the unit matrix. Okay? And it's very nice. You go and work this out, you will find out it's 0. And that's pretty obvious if I know that the matrix can be put in this form, because I'll just have in each of these spots here the secular equation, which gives 0. But there are some matrices that can't be put in this form. Non-diagonalizable matrix, very pathological. Okay, they just won't do it for you. They'll have a few cases of where they get it, and then there'll be some specters left over that it doesn't work. Okay? Still, this is true. And that's a fairly difficult thing to prove. Now, if you can find a proof that doesn't take up a whole other lecture, which is kind of what it is, I'd appreciate it. The ones that I know of are, they're not friendly. Okay? But in any case, this is a key thing to what we want to do with this. New techniques for handling eigensolutions that that are not so well known is what this is all about here. So, what we're going to do is use this Hamilton-Cayley equation in its factored form to write out what we will turn into projection operators. So that's the main the key to getting this this scheme to work here. So the Hamilton-Cayley theorem, that is the Hamilton-Cayley matrix equation of the 0 matrix, is equal to the secular polynomial matrix substituted, is the key idea here. Now, these projection operators are defined in the way that's shown in this particular line of the slide here. Basically, I have a thing called P1, where I simply throw out the factor that goes with the eigenvalue epsilon 1 and keep all the others. Then I go on to the next one called P2, and that's where I drop the second factor from the secular equation. Just put a 1 there if it's a matrix equation. And so forth. I go through as many as I have. If I have an n by n matrix, I will have n of these equations that lack one factor for this this Cayley equation. In our case of our 1, 2, 3, 4, we have a P1 here where we've taken out the factor that involved the eigenvalue 1. Okay, and left it with m minus 5. Okay, so here's the matrix minus 5. And we have the, what I call the unfinished projection operator right here. And we'll see how it is a projection operator fairly shortly here. And then P2, I've dropped the second factor to get it. I'm left with the first eigenvalue subtracted from the matrix. That's the 1 right there being subtracted and giving me this thing. Okay. So that's the numerical example, just for 2 by 2, our favorite 1, 2, 3, 4 matrix. Okay? So, what we we'll notice then is that if you do that, and this is a fancy symbol for doing that, the product here, for projector K over all of the factors involving eigenvalue J except K. So this is just saying leave out one factor, but take all the others and product them. Okay. But there is one caveat, the stuff that we're going to do today, it demands that all of the eigenvalues are different from each other. There is no pair of degenerate eigenvalues. And if you have a degeneracy, it is possible that your matrix might not be diagonalizable. We have to handle that as a separate case. Okay? We're just going to do the kind of matrices that behave the usual way. If you tell your computer to make a random matrix, the probability of getting a degeneracy is essentially zero. That's kind of an interesting fact. Okay. It really takes a lot of waiting. It's like a lottery in the universe to get a degenerate matrix. It's quite the opposite of all of the other things in sociology. Anyway, so this is what's working for us, though, is here is the P for a particular K. That means I took out the kth factor, and then I multiply here by m minus epsilon k. That's the factor I took out of that. That reconstructs the secular product and gives you 0. This is the trick right here, because that then gives you a pk that acts like an eigenvector. That is, this is an eigenoperator. A little pk, just like this one right here, okay? If I take the matrix and multiply this thing by it, it just comes right back to me with the eigenvalue multiplying it. In other words, each of these is an eigenvector. Not normalized correctly yet. We'll do that later. So that's the cool thing here that makes all of this work. We reconstruct the Hamilton-Cayley equation. Okay, so now we do this as elegantly as possible, and that's what the next thing is. Now, one thing. Notice that since pk is made out of polynomial of m, that is products or sums of m, m squared, m cubed, and so on, it is absolutely guaranteed that the matrix itself commutes with each one of these truncated Cayley equations, which are nothing but polynomials of powers of m, okay? So it's absolutely guaranteed that m commutes with this little pk operator. So either side is going to give you an eigen equation. I can put the m on the other side, that is the right side, as opposed to the correct side that we're used to, and still get this p multiplied by the eigenvalue that it's labeling, namely the kth eigenvalue. Okay? So the basic idea is how, m commutes with p. How is that? Well, does m commute with m squared? Obviously. M cubed, m fourth, a combination of those, you're in, right? That's the thing that makes it work. Okay? Does this making sense? Okay, any question about this? Stop, because you lose your train of thought on this, you're not going to get much out of this. Okay, so let's take it to the next level, and that is fix it so these p operators really behave in the most elegant fashion possible. So far, we notice one thing, and that is when I put P1 back together with P2, I reconstruct the Hamilton-Cayley equation, which is 0. So I'm guaranteed that the product of this with that is 0. So what I've found by having this little commutation here is we're going to get both the row vectors that are eigenvectors, and the columns are going to be the ket eigenvectors. And it's not always true that the bras and the kets are nice, clean conjugates of each other. That's the way it is in quantum mechanics, right? That's true for what are called normal matrices. But this is not a normal matrix, this 1, 2, 3, 4 here. So we're going to see the thing working on something that it's not, you wouldn't think that the sort of projection stuff would work. It really does beautifully. Okay, so the idea then is to look at the product of Pj with Pk in general. That is, here's Pj times that product of all of the other factors except for k. So what you end up with, given that the matrix itself is seeing an eigenoperator for all of those little p's, what you're given is this Pj comes in here to the m, okay? And it also comes into that one right there. But on this one, it just gives me a eigenvalue that goes with the Pj, namely epsilon j. So you end up with an equation like that, right there. So here's the Pk being put in there, and then I take this thing out and get just a product of epsilon j minus epsilon m. Now remember, we said these eigenvalues, none of them can be equal to another one. So if this is m not equal to k, as I'm producting through here, I'm going through all of these m's here, and leaving j alone, and we're multiplying by j. And this is not dummy index rule thing here. This is just a particular j that is sitting there. I will get 0 from this product if j is not equal to k. I'm guaranteed to get something that's not 0 if these two things are equal, j and k. So that's what we're going to divide by. We're going to divide by, for this particular operator pk, we're going to divide by the product over all m except k, dividing it out. And that is the next step here, which produces the kind of projection operators that we really want. These are called idempotent projectors, not to be confused by impotent ones. That's something else again. Okay? Or nilpotent ones, which we'll talk about a little bit later. But the word idempotent means that you have an operator, P, that's idempotent, P for P here, which means that if you multiply it by itself, you give it back again. It's like 1. Okay, 1 times 1 is 1, right? But these are generalized ones. So we will build by dividing by this thing here, which is the epsilon k minus epsilon m for all m not equal to k. Well, there's only one other eigenvalue for this problem, so I'm just dividing by here 1 minus the other eigenvalue for this particular one. And remember, we dropped that one factor out to make P1. So this is m minus 5 times 1, which we had before as a little p. This is the big P that's normalized correctly, so this becomes idempotent. And then the next one, this one right here, is the same deal. Okay, this one is the one that goes to the second eigenvalue, which happens to be 5, and then I subtract the other one instead of vice versa for that one. Okay, now these things will again obey the rules that we get 0 when we multiply them by each other, but when we multiply them by themselves, we'll get themselves back again, and that's the cool thing that happens here. So this is the sort of orthonormality relation for operators. And this is part of a general scheme for physics in the sense that we replace states by operators that produce those states. So we're going to be just working with operators here and having eigenvalue and orthonormality and completeness relations for operators that are normally very messy when you talk about states. This is going to clean that up. So we still have, after we've multiplied by this, or divided by this factor here, we still have something that satisfies the eigen relationships, that you can multiply these things by 17 and it's still going to work. But this particular multiplication gives us a working eigenoperator equation for an idempotent projector that makes it so that it's really powerful mathematically. So that's the basic thing that we're working here, is the eigenoperator for orthogonal operators. Now, the next thing is, we've just shown orthonormality in a sense. A completeness relation is the key to what we're going to do next. But just let's stop for a minute here and look at what we've got. Here's the big P1 for this 1, 2, 3, 4 matrix. Here's the big P2. This one we divide by 1 minus 5. This one we divide 5 minus 1. Okay, both of those are 4 or minus 4. And so I end up here with this idempotent operator. And then you can do a funny thing. You can basically just take the square root of the numbers that you have here and multiply it by a factor and then divide by that factor. So you can put any number in here and still get the same thing. But basically you make an outer product of two vectors. You make something that Dirac would love. This is a ket bra. In quantum mechanics you see these all the time, but now we've already produced one. We produced the operator. You just have to write it in the direct product notation, which is the first number is this times this. That's this number right here, 1/4. Okay. The next number here is this times that. It's minus 1/4. Then down here I've got a minus 3/2 to go through, multiply each one of these things. There's the minus 3/4. That's this times this. And then there's the 3/4. So this is something that's pretty easy to do just by sight. You can put any factor on this one you want to. I can get rid of the 2 and put a 2 here as long as I put it down here. Make these guys all 4s. So this is right where you produce eigenvectors. And remember, in an spectral decomposition is what we're really talking about here, but in an eigenvalue, an eigensolution problem, most of the physics information is in the eigenvectors. You got n states, okay? You only get n eigenvalues. Those are levels, right? But the vectors contain n squared, because you got n of them, and each one of them has n components, right? So you got n complex numbers sitting there trying to tell you something. So the eigenvectors are things we want to handle skillfully. That's where the physics is. Eigenvalues, well, they give you some beat frequencies and stuff like that. But the stuff inside there is really giving you the form of the wave that you've produced. Okay, so here's where we stand on this. Let's take it to the next step and just go and graph it out so you can see what it is we're talking about here. So here's the projectors for this matrix, 1, 2, 3, 4. Okay, there's the P1 sitting right there. Got it right there. Okay, and what I've done is pulled the eigenkets and the eigenbras out separately, just so you can look at them. Okay, so we've got a guy here, this epsilon number 2. Okay, that's this guy right here. Okay, that's this guy right here. Okay, 1/2, 1/2. Okay, so that's about the second one first, coming down from the top. Meanwhile, there's this guy right here. Okay, this is 1/2 minus 3/2. That's the eigenket number 1. Okay, out 1/2, down 3/2. All right, very different from this one. You see, this is not a symmetric matrix, so they don't end up on top of each other or conjugate of each other. Then these bras here, okay, like this one, the second bra and the first bra, which is right here. Okay, first bra is 1/2 minus 1/2, 1/2 minus 1/2. Okay, and then this guy right here, 3/2 is the first component, and 1/2 the up component. Is that clear? You got it there. Okay. You've seen this before, covariant and contravariant, right? This guy right here is orthonormal to that guy who's got a different number. And the same thing's true of this guy right here is orthonormal to the other guy that has the number 2. This is the number 1 bra, it's a row vector. This is the number 2 ket, which is a column vector. Okay? They're orthogonal to each other. We've already proved that with these Hamilton-Cayley equation, basically. Okay? You see how this gets powerful, and it's a really nice way to see what you're doing in a problem that involves operators that aren't normal. Normal meaning normal for quantum mechanics. Okay. All right. Well, let's put that over here so that it's showing clearly. And then the other thing to notice when you're doing this, let's take it right here, is the actual, shall we say, matrix for bra 1, ket 1, bra 1, ket 2, and so on. It's just unit matrix. Okay. Now that's one way to get a unit matrix out of this, but there's another way that's really, really spectacular. And that's the one I definitely want to show you here, coming up here. It's the sum. You take these two operators right here and here, okay, and sum them up. 1/4 plus 3/4, that's 1. Minus 1/4 plus 1/4, 0. And let's look at the diagonal component down here. Again, 3/4 now plus 1/4, again, 1. The sum of these things is a unit matrix. Yes?
So if we do this bracket, epsilon
The
1
factorization.
Yeah, and then on the graph, how will it look like? How will it transform the vectors which are there, the red vector and the blue vector, right? So I can combine them to make it unity, right?
Add this one to
Yeah, but then on the graph,
this one.
on the graph, will it cause any change in these two vectors, this blue one and the red one above it?
Mm-hmm.
So they will combine to give a scalar, right? So,
You mean if you took the product of these two,
yeah.
right? This guy with that guy. That's what's really cool about this. And then you go this guy with that guy. Doesn't look like it's going to happen, right?
Yeah.
But because this one's got inverse to that one, bingo, scalar product is 1. Good question. Isn't that neat? There's a lot of nice things that you take for granted after you get used to this stuff, but it's still amazing.
And because it's clear if you take the product of those two which are perpendicular to it, they'll give you 0. But
Oh, you can see that very clearly by this little square here.
yeah, but
Right.
in the other two it's not.
The other two, not 0. In fact, 1. Yeah. So you either get 1 or 0 from all of the products in this is a really simple metric, right? Remember, we had a covariant metric and contravariant metric, and then we had the Strontian matrix, which was made circle, right? And that's what this is. So we get that right off the bat and make use of that forever. Okay? So we've got mutually orthonormal projectors and vectors that go with them. And then we've got ket-bra combinations, which are the projectors summing to 1. Wow, that turns out to be powerful. That is really what some people call the cat's meow. And this is the just summing it all of that up. This is what we call the spectral decomposition of an operator. Because if I take this relation right here and multiply by the original 1, 2, 3, 4 matrix for us, but in general matrix M, each time it hits one of these projectors, it just gives an eigenvalue. Wow, that's cool. And basically, you can see that happening right here. This matrix is the sum of 1 times the the product up here is P1, and then 5 times this P2, okay, 1 times this guy, appropriately normalized. You gotta keep that 1/4 and you gotta keep the 5, okay, or this isn't gonna work. But as long as you use the stuff that we've got written right here, or use Dirac notation, you see, and we're getting Dirac notation kind of in the bargain here, you're going to get the matrix, the original matrix. Okay? Now that's just the spectral decomposition. As you see on the wall up there, 3rd slide in, there's something else that is really the reason for doing all of this. And that's what I call the functional spectral decomposition. So let's put that up here, just for the sake of the wow factor. I can take now any function of this matrix by simply evaluating, in our case, 2 points on that function. That is, at each eigenvalue, I look up whatever that function's going to give me and put it down next to the P, and I am done. I have made a matrix that is, represents the function of that matrix. That is really something. Now suppose I stopped right now and said, I want you guys to find the 50th power of the matrix 1, 2, 3, 4. Just like the what's alleged to have happened to Gauss when the teacher wanted to go look at, read a magazine or something. He was tired of the class, and so he had to ask them to add up all the numbers from 1 to 100.